The first part of yesterday's lesson is understanding that there's a relationship between an exponential function and its inverse. When you take y equals 2 to the x, which is an exponential function, and you say, well, what's the inverse? You swap x and y, and you get x equals 2 to the y. So this is the corresponding logarithmic function, but the other part of the lesson is not only understanding that, but understanding how you can write x equals 2 to the y as y equals. And it's y equals the base 2 logarithm of x. That's pretty much it. That second point I made can be extended to any letters or numbers, that you should be able to go from something like p equals log base q of r, knowing that the logarithm is p, is telling you the exponent is p. So when you write it in exponential form, it's q to the p equals r. Does anybody have any questions? I'm sure you do. Go ahead. 22, certainly. So by the time you get to questions like 21, 22, 23, 24, these are starting to become more challenging and more exam-worthy. You have log base 3 of m equals n, and you want to determine log base 3 of m to the 4 in terms of n. So if I rearrange this, and I'm not sure why I'm doing this. I'm just saying when I see log base 3 of m equals n, I want to explore what that's telling me in something that's meaningful, and that's meaningful to me. That's telling me that 3 raised to the n, should have looked at it more closely, that's telling me that 3 raised to the n is equal to m. When I write that in exponential form. So over here we have log base 3 of m to the 4, which is 3 to the n to the 4. So now we have log base 3 of 3 to the 4n. And part of this question, for me anyway, because I know something you don't know yet, is a little more challenging for me to explain to you because I want to do it a simpler way. In a couple of days of classes, there will be an easier way. And now what we have to recognize is that this logarithm that I've written, log base 3 of 3 to the 4n, is saying, to what do I raise 3 to get 3 to the 4n? And the answer is 4n. And, you know, reasoning out, I get 4n because I'm saying, what is it that I raise this 3 to get this whole thing? So I reason out that I have to raise 3 to the 4n to get that whole thing. But just in general, this is always going to be the case. When you take a logarithm with a particular base of a power of that base, the logarithm of the power of that base is equal to the exponent, always. Is that okay?
Yeah.
Other questions? Go ahead.
8.
8? So y equals 5 to the x, and I pause there because I think what you should do as well is if you're given a question with function notation, immediately say to yourself that I could write that as y equals. It may be helpful to do that, or it may not be. I'm just saying that's what it is. What is the inverse? Well, the inverse is found by swapping x and y. But we want to write things in terms of y. So perhaps a student looks at this and immediately knows what y is equal to because it's an inverse of an exponential function. If not, you say to yourself, I don't know what this means, so I'm going to change it to the other language, which means I'm going to convert it from exponential to logarithmic. So it's going to be a log base 5 of something equals something. And the general idea or rule is that whatever thing is with the base in one form is away from the base with the other form. So the x is not with the base, now it is. That's the equation of the inverse. And we can write this. I don't want to spend too much time reviewing previous parts of this course right now with you, but if you were to graph y equals log base 5 of x, you would get a function, so we can use function notation. What are the characteristics of this? Well, we're going to talk more about this today. This is going to be crucial for today. In order for me to visualize what this function looks like, I go back to the exponential function at the top of the screen. Because I know y equals 5 to the x looks like this, very roughly, with a y-intercept of 1. And it happens to have a horizontal asymptote on the x-axis. I don't know about you, and by you I don't mean you specifically, but you as a group, but how many of you can visualize that when you reflect that, it looks like this? So there's no need to pick specific points and switch out x and y and replot them. This is that function. So what are the properties? What is the domain of that function? The domain of that function would be x is greater than 0. The range would be y as any real number. There is an x-intercept of 1 because there was a y-intercept of 1 on that, which we learned on day 1. There is no y-intercept because this is a vertical asymptote, speaking of which the equation of that vertical asymptote is x equals 0. Does that help? Okay. Yeah. That's fine. 24? Again, bear with me because there's probably a simpler way to do this, but you don't know the rules yet. So I'm going to take this first equation and rewrite it as 2 to the m equals n in the hopes that I can make use of that. And I hope that you see what we really have are two equations with two unknowns. This is a system of equations in some way. So what I could do to solve this equation here is I could take this and put it in for m, because that's what m is equal to. If I did that, I would get 2 times log base 2 of n plus 1 equals log base 2 of 16n. And I hope that everybody in the room understands this, at this point in time, is a dead end. It's what I would do later on with you if you knew some other rules. So that method of substitution is no good. It doesn't lead anywhere. What may lead somewhere, though, is taking this and putting it in here. Because n is 2 to the m, and I have an n in the second equation, so I'm going to put 2 to the m there. What happens? I get 2m plus 1 equals log base 2 of 16 times 2 to the m. Now, what this is, and I'm afraid I'm going to have to write this out because I want you to see the words, is this is the exponent that 2 is raised to get 16 multiplied by 2 to the m. Now, I know that this isn't an equation we're solving at this point, Kendra, but just forgetting about the left-hand side, if I try to crack this problem, I'm saying that 16 multiplied by 2 to the m is 2 to some exponent. And that exponent is what that whole logarithm is. The logarithm is the exponent to which you raise the base to get the argument of the logarithm, to get what you're taking the logarithm of. So, well, I can write everything with base 2. I can write this as 2 to the 4, this is 2 to the m, and this is 2 to whatever this whole thing is equal to. Right? That question mark is this whole thing. And now I can say that I add the exponents when I multiply a common base, so this is the following. Which means that it must be 4 plus m. So, and I'm going to show this to you here. This is 4 plus m. And that is saying that 2 to the 4 plus m is the same as 16 times 2 to the m. And we can see that because 16 is 2 to the 4. So I guess I'm just showing you that when you add these exponents, you do get this exponent. Almost seems like we're going in circles here. Now what we have is this is equal to 2m plus 1, and I can solve that for m. I don't know what I want to find yet, probably m and n, I would guess. So I subtract m from both sides and get m, subtract 1 from both sides and get 3. Now I can go back to any of the equations I started off with, maybe this one, right here. If m was, did we just say 3? If m is 3, then n is 2 to the 3. Be careful with that 2 to the 3. That's 8. Is that okay? Okay. Again, after Monday's class, Mondays? Yeah, probably after Monday's class, there might be some ways for us to take a more direct approach. Other questions? Sasha? 12D. So we are asked to find x when we have log base x of 16 equals 4/3. I write that in exponential form, and I get that. Now, are you okay with that move? Okay. So yesterday when I introduced logs, I was asking the same question I asked a lot with trig. How many of you kind of intuitively see what the answer is? And those people that immediately intuitively see what the answer is in this unit, that's going to fail you sooner or later, and it probably starts to fall apart right now, is it's not entirely clear what x is. So we develop a rule that says, I want to get x to the 1, because that's x. And the only way to accomplish that is to raise this side to the 3/4, which is the reciprocal of that exponent. And the reason for that is that if I have x to the 4/3 to the 3/4, I multiply the power of the power. And by the way, I need to raise this to the 3/4 as well. And what I'm going to get as an exponent on the power of x is 1. Because when I multiply a fraction by its reciprocal, I get 1. So I end up with x to the 1 equals 16 to the 3/4, which, by the way, means the 4th root of 16 cubed. And I think it's important that you know that. It's not just a matter of putting it into your calculator. When you have a fractional exponent, the denominator is a root of the base. The numerator is a exponent applied to the base. 4th root of 16 is 2, because 2 to the 4 is 16. 2 cubed is 8. Good. Other questions? McKenna? Say 14a. What is, and listen to how I say it, what is the base 2 logarithm of the base 3 logarithm of the base 4 logarithm of 64? So these are embedded things. If I said to you, what is the square root of the square root of 256, you would focus your attention on the inner thing, which is root 256, and you'd say that's 16. You could work it out. And then that becomes the square root of 16. Then you could focus your attention on the inner part, and the square root of 16 is 4, so you'd end up with root 4, which is 2. Now this is a little bit different than what we have because there's only one type of square root. But here we've got base 2 logarithms, base 3 logarithms, base 4 logarithms. However, what is the base 4 logarithm of 64? Well, it is the number to which we raise 4 to get 64, and 4 cubed is 64. And if you don't know that immediately, then I suppose you have to take your calculator and go, well, is it 2? 4 squared is 16? No. Is it 3? 4 cubed? Oh, yeah, it's 64. So that is 3, and now we have log base 2 of log base 3 of 3. Well, log base 3 of 3 is the exponent to which you raise 3 to get 3, which is 1. 3 to the 1 gives you 3. So now this is log base 2 of 1, which is saying to what exponent do you raise 2 to get 1? And the answer is 0. 2 to the 0 is 1. And you would do the same thing for d, by the way. This is a base 10 logarithm because it doesn't say. So log base 10 of 10 to the 16 is saying to what do you raise 10 to get 10 to the 16? 16. Then it's log base 2 of 16. To what do you raise 2 to get 16? 4. Then it's log base 4 of 4, which is 1. All right. We're going to move on now. And there are a couple of different things in this lesson that I've put in. It's mainly about transformations of logarithmic functions. But we're going to be looking at applications of logarithmic functions and learning about something called the change of base formula. The lesson today, or the class today, started off with somebody asking about graphing a logarithmic function, or finding an inverse and graphing a logarithmic function. If you know what the logarithmic function looks like, you ought to be able to apply transformations to it, just like we've done with other functions. So use transformations to sketch the graph of this function. Now, this function is a transformation of y equals log base 3 of x. So there's two camps here of people. The camp that immediately knows what y equals log base 3 of x looks like. And I'll remind you that if you have discovered how to do this on your graphing calculator, or when I do show you, your graphing calculators do a lousy job. Okay? They do not give you a nice diagram. There's the camp of people that know immediately, for example, that this logarithmic function will have a vertical asymptote here. It will have an x-intercept here. And because it's a base 3 logarithm, if I go up 1 for y, I triple. If I go up 1 more for y, I triple. There is going to be a group of people who, if you don't have that now, you will very shortly. So this is what the function looks like. And by the way, this would be at 1/3, and I'm not going to worry about drawing that. So this is what the original function looks like. Now, you do need to know that that's what the original function looks like. So how do you know that that's what it looks like if you just don't automatically know? You have to go back in time and say that this function we're trying to graph is the inverse of y equals 3 to the x. And hopefully you have a better handle on what y equals 3 to the x looks like. And I'm going to draw it, but if I were doing this with a student side by side, I would say draw it, but then erase it. You're only drawing this function y equals 3 to the x so you can see what this function looks like so that we can transform this function to get the function we're asked about. So what you would do with pencil and paper is you would say, well, I know that 3 to the x has an asymptote here. Your brain would immediately say, since it's the inverse, log base 3 of x has a vertical asymptote on the y-axis. You would start plotting points on 3 to the x and saying, over 1, triple, over 1, triple. And then you would start to piece the new function log base 3 of x together using reflecting those points. Am I making sense here, or are you with me? But ultimately, what I would say to you is, we start off with that function. So when you're working on this on your own and you say to me, Mr. Way, how do I know what this looks like? My answer is going to be graph y equals 3 to the x and then use it to find the inverse, which is log base 3 of x. However, again, I know I'm repeating myself, but I expect you to know that this is what y equals log base 3 of x looks like. Now it's just a matter of identifying a, b, h, and k and deciding on transformations. Everybody take a minute, someplace where you have some white space, and write down what you believe the values of those 4 parameters are equal to. Okay, and what's the value of a? 1. Because the function is log base 3, and it's just 1 log base 3. I'm going to stick with you, Caden. What is the value of b? 1 as well, because b is the coefficient of x in the argument of the function. And what is h? -9, right? So h is the number that you would take away from x to get the argument, which is x plus 9, and k? 2. Look, all we have to do is take this graph and shift it 9 units to the left and 2 units down, or 2 units up. That's it. But would you agree that it doesn't matter how many units this thing is shifted up? The asymptote here will stay the same? Would you also agree, though it's not important here, if I were to stretch this function in any way, horizontally or vertically, the asymptote will still be there? And if I were to reflect this function in any way, the asymptote will still be there. What's the only thing here, Sasha, that would move that asymptote? H. So if h is -9, the asymptote is automatically going to be at that h value. It has to be. And now we can start shifting. And I'm going to do this in 2 ways. If we take this point here, and I shift it 9 to the left, it's going to be here, which shouldn't be a big shock to you, should it? Because it's 1 unit to the right of the asymptote. And I really ought to have left this asymptote over here. And then I move it 2 up. If I take this point and I move it 9 to the right, look, I'm not even going to count what that is. It's going to be 1 above the axis and 3 away from the asymptote, and I move it up 2. And, whoops, yeah, that's right. And I just want to point something out to you. Once you know this leading point, you can plot all the other points by asking where they are relative to that point. When I compare this leading point on the original function to the next point is over 2 and up 1. Over 2 and up 1. From there, I can go over 1, 2, 3, 4, 5, 6 and up 1. 1, 2, 3, 4, 5, 6 and up 1. Look, I'm just giving you some strategies here. You have a number of different tools at your disposal. You have to translate those 9 to the right and 2 up. So we are going to get a graph that looks something like this. That's what it looks like. What are we asked? We are asked the equation of the asymptote. It's a vertical asymptote at x equals -9, which is x equals h. The y-intercept, now we lucked out, because if you look at your graph, one of our key points was right on the y-axis. But yes? Okay. A y-intercept is where x equals 0. So if I load 0 in here, that's the y-intercept. 0 plus 9 is 9, so I get y equals log base 3 of 9 plus 2. Well, log base 3 of 9 is 2. Because log base 3 of 9 is the exponent to which you raise 3 to get 9. That's 2. 2 plus 2 is 4. Well, that's what it was. To find an x-intercept, y is equal to 0. So we do the same thing, and we get 0 equals log base 3 x plus 9 plus 2. And don't let this scare you. You're just going to unwrap that. You're going to subtract 2 from both sides and go from there. So if I subtract 2 from both sides, I get -2 equals log base 3 of x plus 9. Now I have to peel off that log base 3 operation. How do I do that? I write it in exponential form. That's it. I write this as 3 to the -2 equals x plus 9. And I can subtract 9 from both sides. And that's the x-intercept. 3 to the -2 is 1 over 3 squared. So you can work that out. -72/9. No. -73/9. I'll just shout out random numbers until I get it. What is it? -89. That makes sense. Now that I know the answer, that makes sense. -89, which is, correct me if I'm wrong, -8.99999. Okay. 88888. Okay. So when you take a look at the graph, you can see that that's going to be a very, very accurate result. And we have one more thing that we want to do, domain and range. Well, the range will always be y is greater than any, or y is any real number rather, because logarithmic functions go up and down forever. And the domain would be x is greater than whatever that h value is. I had asked a similar kind of question in one of the first lessons in this unit about range with exponential. I'll ask it about domain here. That is x is greater than h. Do you suppose we could ever get x is less than h? What would have to happen there, Annalie? Or a horizontal reflection. We would have to have a negative b, and that would cause it to move the other way. Let's just do this one without actually graphing it in perfection with points. This is y equals negative log base 2 of 2x plus 6. Can everybody take a minute, please, and determine the values of the four parameters a, b, h, and k? I hope we would all be in agreement on those three. What is the value, Isaac, of h? 3? Good, negative 3. We do have to factor that 2 out to end up with negative log base 2 of 2 and then brackets x plus 3. So h is negative 3. So you might find some room to do this. I don't want to draw this right on here because, as I said, I just want to draw a rough diagram. So if I were to take a look at log base 2 of x, log base 2 of x looks like that. What's one thing that happens to this function? Well, it reflects vertically. That means it's going to look like this. What's another thing that happens to it? It stretches horizontally by a factor of 1/2 because b is 2. So what that is going to do is cause this to be even closer to the y-axis. The only other thing that happens is it shifts 3 to the left, which means we're going to have a vertical asymptote over here at negative 3, and the graph will look something like that. Let's determine the equation of the asymptote. Well, it's x equals h. What's the domain and range? The domain is x is greater than h, and the range is y is greater than, sorry, I keep saying greater than, y is any real number. Now, how do you determine, let me write out the function again. The y-intercept, well, the y-intercept would be negative log base 2 of 0, 2 times 0, plus 6, which is negative log base 2 of 6. But you don't know how to find log base 2 of 6. You don't. You just know that it's a number somewhere between 2 and 3 because log base 2 of 6 is the exponent to which you raise 2 to get 6. And 2 to the 2 is 4, which is not 6. 2 to the 3 is 8, which is not 6. But somewhere between 2 and 3, we will get 6. So all we know here is this y-intercept is somewhere between negative 2 and negative 3. And if you look at the graph, that would certainly make sense, that we're going to get a y-intercept that's negative. So what are we going to write here? The y-intercept is at negative log base 2 of 6. What is the x-intercept? The x-intercept is found by making y 0 So how do we solve that? Well, I'm going to multiply both sides by negative 1 to get rid of that negative. I'm going to write this as 2 raised to the 0 equals 2x plus 6. And now it's a simple thing. 2 to the 0 is 1. So we end up with 1 equals 2x plus 6. You can solve that for me now. Subtract 6 from both sides and divide by 2, and you get negative 2.5. I think. So the x-intercept is negative 5/2, comma 0. I would say that the thing that you're getting practice with today more than anything so far is not the transformations, it's finding the x and y intercepts. Although this is, in just a minute, you're going to know how to find that. Okay. Don't worry about that. Example 3. In each case, the red graph is a transformation of the blue graph. So the red graph is a transformation of this. What do we do to the blue graph to get the red graph? Well, this point is 4 away from the y-axis, and now it's only 1 away. So it appears as though we're stretching things horizontally by 1/4. Are you with me on that? Sensing maybe it's just a Friday afternoon vibe. Are you guys with me here? Yeah. It's a great, absolutely, that's a great point. The asymptote, it's implied here, the asymptote has not moved. If we took this blue graph and moved the whole thing 3 to the left, there would be part of it over here. So what we would do is we would assume that to go from the blue to the red is a horizontal stretch by a factor of 1/4, which means b is 4, and that gives me y equals log base 4 of 4x, and that's the answer, but I'm making a note because on Monday I want to come back to this question and show you something else. Are you guys okay with this? Like, are sensing like a apprehension? What's that? It's Friday. It's the Friday blues. Until you leave school, then it's the Friday woo. Okay, all right, I get it. What about this one? We want to go from log base 4 of x to this red graph. Well, there's a vertical reflection, so a must be negative, and that blue point is 1 above the x-axis. When we reflect it and look at where it lands, it's 3 below. So it must be stretched by a factor of 3, which means the new function is y equals negative 3 log base 4 of x. And in line with Kendra's comment about how do we know it's that type of translation and not something else, you can see that this point doesn't move. And if that point doesn't move, it's invariant. Vertical reflection would have it be invariant. Okay, so determine the domain of this graph. Listen, all you have to do is recognize that h is negative 4. Everybody give some thought as to why h is negative 4. You need to take that log base b of 3x plus 12 and factor the 3 out. Then you can see that h is negative 4. Why am I doing that? Because that tells me that the vertical asymptote is at negative 4. Since b is positive, by the way, when I talk about b here, I'm talking about this b, not this b. Just 1 second. Since it's positive, that means the graph still kind of opens to the right. So the domain would be x is greater than negative 4. Go ahead, Kendra. Oh, you don't have minus 5? Does it matter? And I'm not being sarcastic. I'm asking a sincere question. Does the vertical shift matter? No. And I suspect that when I made up the notes recently, I thought, well, let's throw in a vertical translation as well. And by the way, this 2 in front doesn't matter. I could even put negative 2 in front. it would flip it upside down, but it would still kind of go off to the right. Have I answered your question? Okay. So you can put in -5 or not. Yeah.
Horizontal stretch factor doesn't really matter either?
It won't affect the domain. The horizontal stretch factor of 1/3 is going to take this graph and cramp it in closer to that asymptote before we move it. But it's still going to be on the right-hand side of the asymptote. And even though the green graph is closer to the asymptote than the brown graph, when you head downwards, they both get infinitely close anyway. Okay, so now we're going to learn about something called the change of base formula. This is on your formula sheet. And it is a way to change any base logarithm to any other base logarithm. So for example, log base 2 of 6, if I want to change it to a base logarithm that I can use my calculator for, I can change it to base 10. So I have log base b of c. I'm going to change it to log base 10 of c and log base 10 of b. I introduce an entirely new base, 10. The big number, 6, goes on the top. The little one goes on the bottom. Remember we had an x-intercept or a y-intercept? I guess it was a y-intercept of negative log base 2 of 6. Well, do you remember we said it was somewhere between -2 and -3? Log of 6 divided by log of 2 is 2.5849. So, and there was a negative in front. So that was the intercept. So how would we evaluate log base 6 of 24? You'd go log of 24 over log of 6. It's about 1.77. Log base 3 of 66 would be log of 66 over log of 3. About 3.81. I mean, I hope you understand that I'm not writing down the exact values because I can't. It turns out they're irrational numbers. It's like trigonometry that way. Log base 10 of 3, well, I don't need to use a change of base formula there because I have a log base 10 button. I could go log base 10 of 3 over log base 10 of 10. I'll still get the same number. Log base 20 of 5 would be log of 5 over log of 20. 0.5 something. So you can put these in order from least to greatest. How this would be on an exam is you would have these labeled as 1, 2, 3, 4, and it would be a numerical response question. So you would put 3 first, then 4, then 1, then 2. Are you with me on that? Okay. Now, everybody in the room is lucky. See, I got this old calculator, but you have something that is fancier. If I go to my math menu and I scroll down here, I don't see anything that's really to do with logarithms. But if I go to an 84, even an 84 with this horrible faceplate, and I go math and scroll down, I got something called log base. And when I hit that, I get that. Now, some of you with a TI-84 may not see that. I'm going to ask you in a second if you do or you don't. But if I want to know what log base 6 of 24 is, I just do that. It's not going to be helpful for written response maybe where you have to use the change of base formula in an equation. But when it comes right down to it, it's pretty easy. Does anybody have a TI-84 where when you go to the math menu, you're missing log base? All right, that was easy. Because if you are, then we just have to transfer an operating system to your calculator. We have to upgrade it, that's all. And that's allowed. Okay, a couple more questions. These are quick questions. Most welding glasses now are electronic in nature. But there was a time where you'd put on a welding helmet and there was a little window and you would clamp in there. It's called a number 14 welder's glass. And if you had that going and you tried to walk around in the world, you couldn't see anything because it blocks so much of the light. And that's because there's a huge amount of bright light in welding. It turns out that the shade number of a welding glass is equal to this, where T is the proportion of light that makes it through. So if T is 0.333, 33.3% of the light gets through. And the question is, if you want to watch a solar eclipse, you'd need to look through a number 14 welder's glass unless you wanted the sun to drill holes in the back of your eyes. What fraction of light is allowed through that? So what this question is asking you is, what's the solution to this equation? And I'm not even going to show you the steps on paper. I'm going to do it on my calculator. Before I can start peeling away the layers that surround T, I have to get rid of that 1. I have to take 14 and subtract 1. Okay. So now I'm left with 13 equals 7 times negative log of T over 3. So I got to get rid of that 3. I'm going to multiply by 3. I have to get rid of the 7. I'm going to divide both sides by 7. And now I have this. I have this number equals negative log of T. That's where I'm at. I've subtracted 1, I've multiplied by 3, I've divided by 7. So let's switch both sides to this equation and get log of T equals negative 5.57. You could just multiply both sides by negative 1. Who's in chemistry 30 right now? Have you done acids and pH yet? Okay. How am I going to find out what T is from this? This is the thing that even good students, they get here and they go, what now? Sasha? Right, because don't forget this is log base 10. T will be 10 to the negative 5.57. Interestingly enough, I could, here's my negative 5.57, I could go 10 raised to my answer, couldn't I? But instead, I can go inverse log and look what pops up. To get rid of sine, you go second sine. To get rid of log, you go second log. Either way, this is the proportion of light that gets through, which is 0.000000268. It's a proportion of light that gets through. In other words, hardly any light gets through, which is what makes it safe to look at the sun through. I just want to put this whole thing up here so we can see what we solved. Any questions on getting that answer? Let's do one more. Yeah.
Would we get a
Possibly, but very rare. Usually if it's an application, like for example, it turns out science and math is weird. You know when you crack an egg, there's the white of the egg, right? There's the yolk and the white. But have you noticed that the white has two parts to it? It has that, there's two types of, it's called albumin. There's that thin white, and then right around the yolk there's a thicker white. If you've ever tried to separate whites and yolks, you find that the white comes off very quickly, but then there's this gelatinous white that sits there. If you crack an egg on a flat surface and you measure the height of that center jelly part, not the yolk, but the middle part, there's an equation that uses logarithms, seriously, and that height to find out how much protein is in that egg. And it's very close. There's a formula if you take the mass of a jackrabbit and you put that into the formula, and it's a logarithmic formula, it will tell you the metabolic rate, which has to do with the biology of the jackrabbit. This next example that I'm going to show you, I thought it was made up. I thought some math teacher thought, oh, I'm just going to make this up. Let's read this. It says there is a logarithmic relationship between butterflies and flowers. In one study, scientists found that the relationship between the number of flower species in a region is connected to the number of butterflies that are in the region by a logarithmic equation. The number of flower species is equal to negative 2.641 plus 8.958 times the common logarithm, the base 10 logarithm, of how many butterflies are there. How many butterfly observations are there with 25 flower species? So we're going to solve this in a second, but this is the equation you're asked to solve. But before we do, I read that and I thought, come on, you're just making stuff up to try to make math more interesting. So I found the study. And literally what it involved is introducing more species of flowers and coming back a few days later and checking out the number of butterflies that are there. And removing some species of flowers and coming back a few days later. And this is what their graph looks like. It's logarithmic, there's no question. It looks like it's starting at 0 here, but it's very, very close to 0. There's an asymptote that's on the y-axis. It's very, very close. Now, you have to admit, butterflies do not know what the mathematical relationship is. So it's not a perfect fit, is it? But if you've done any work in science, particularly maybe in Science 30 with me, and Physics 30 with me, you understand that we use equations to model behavior, and it's never perfect. So how are we going to... I think that's kind of cool, that there's a mathematical relationship between how many butterflies and how many types of flowers. How are we going to solve that? Well, we have to add 2.641 first. Then we have to divide by 8.958, and then we have to figure out what to do to get B. Excuse me. So we're just going to take 25 and add the 2.641, then divide by the 8.958. That will give us a number equals to the log base 10 of how many butterflies there are. 25 plus 2.641. Divided by the 8.958. So I'm getting 3.085 equals log base 10 of B. And again, 10 raised to that number will give you B. So 10 raised to that number. Now, you can't have part of a butterfly. Well, I guess that's not true. You could have part of a butterfly. But, you know, what we're talking about here is an estimate. So if you saw this on an exam, it might say rounded to the nearest 100. So you would say 1,200. We'll worry about that when the time comes. I'm just going to round to the nearest butterfly and say approximately 1,218 butterflies. The lesson that goes with this, you're going to have about 15, 18 minutes to work on this. The lesson that goes with this has some, or the assignment that goes with this lesson rather, has some basic transformation type stuff, a little bit of x and y intercept stuff, and then a few problems where you're given an equation that has logarithms in it and you have to use it in some way. Unlike exponential, unlike trigonometric, you would never have to come up with the equation for an application if there were logarithms involved. I do want you to add number 13 to the list of problems.